we will have Professor Richard Walker visiting us from the University of Maryland, who goes by Rich. Rich obtained his bachelor's degree from the College of William and Mary. He then was awarded his master's and PhD from the State University of New York, the Stony Brook campus. He then was a postdoc at the National Bureau of Standards, which is the modern day NIST, and was also a postdoc at Carnegie for a while before he was snapped up by the University of Maryland, where he became a tenured professor and then is now a distinguished university professor. In addition to this and many other awards and accolades, he was elected to the National Academy of Sciences. The reason why we're having Rich visit us today is because if you want to learn about siderophile elements and their isotopes and what they tell us about terrestrial and extraterrestrial materials, this is a scientist you'd want to speak to. So he is going to tell us a little bit about the siderophile elements, the iron-loving elements, and why they really are the geochemical superheroes of the world. I would say a lot of Rich's work has been underpinned by mastery of the analytical chemical techniques. So that is wet chemistry through mass spectrometry. And I think we're going to learn a little bit about this today. So if you please welcome Rich, he will take over from here. Thank you for joining us.
Let me set my timer. Don't want to go over. I hear bad things happen if you go over. All right, well, thank you, Kath, for introducing me. I've worked most of my profession. Does the microphone work?
It works. It's only for the camera, though.
Yeah, okay. So I've done most of my professional career working with siderophile elements. So this is a bit of an overview of some of the work that I and my colleagues have done, and also I'll try to inject a bit of history into the discussion. So let's see. It's not advancing.
It should be. Is it on?
Okay, well, I've only got one slide, so that's all. Thank you very much for the invite.
Well, I can't get rid of that, Drew. Matt, if you can. There's a floating thing. Sorry about this, Rich. Yeah?
Yes, you may try.
So what I would do is I just use this one.
No, I don't want laser pointer. I wanted to advance the slide.
It's not seeming to work.
Huh?
It was 2 minutes ago and it's not now.
I tried to check it quick before it started. I couldn't get it to work either.
Ah, okay. My time is dissipating fast.
Oh, good Lord.
That would...
I think it's on this home screen. Yep, sorry, you have to press the space bar.
Space bar, yes, I can press the space bar. All right, we're good. So what are siderophile elements? Siderophile elements are elements that prefer to partition into metal rather than silicate or atmospheric conditions. And the knowledge of siderophile elements goes back well into the early 20th century. And so I've got on the right-hand side here a abstract from a lecture that Goldschmidt gave in 1937, in which he divided the world of elements into different categories, including siderophile and chalcophile. And so in the siderophile element category, you can see such elements as ruthenium, osmium, iridium, molybdenum, and tungsten. And we'll be talking about some of these elements as this talk proceeds. Also, it's not important for this talk, but certainly some of the siderophile elements are also chalcophile, so they go into sulfides. All right, I'm going to divide the world of siderophile elements into two categories. There's actually three categories. The third would be slightly siderophile elements, but nobody really likes slightly siderophile elements because they don't really do anything special. So we're going to look at moderately siderophile elements, or MSEs, and they include such noteworthy elements as cobalt, nickel, tungsten, which we'll get back to, germanium, gallium, and molybdenum. And I'll also talk about highly siderophile elements, and they include rhenium, osmium, platinum, palladium, and gold, some of your favorite metals. Now, moderately siderophile elements are typically defined as having low pressure metal silicate distribution coefficients of something on the order of 5 to 1,000, and highly siderophile elements, at least at Earth surface conditions, have distribution coefficients greater than 10,000. So they really, really like to go into metal under low pressure conditions. All right, so the mass balance of siderophile elements in the Earth is an important constituent of this talk. Most of the siderophile elements of this planet are sitting 2,900 kilometers beneath your feet in the core. So that's why an element like gold is a precious element, because most of it's sitting in the core. And roughly about 90% of all of the moderately siderophile elements and about 98% of the highly siderophile elements are sitting in the core. And we know this just from mass balance constraints. So we think we know what the concentrations of these elements are in the silicate portion of the planet. If we assume that the planet has an overall chondritic bulk composition, that's where these numbers come from. So I'm going to try to cover 3 topics today, and these 3 are really good topics, but we could do more if you wanted. I'm going to talk about the origin of siderophile elements in the Earth. So I'm specifically going to be talking about the origin of the siderophile elements that are here with us in the silicate portion of the planet, not so much the core. We're going to talk about tungsten isotopic heterogeneity in the modern mantle. In this case, I'm going to be talking about tungsten, an isotope that is a decay product of a short-lived isotope of hafnium rather than mass-dependent tungsten isotopic compositions. And if we have time, we'll end up spending a little time talking about the molybdenum isotopic composition of the silicate Earth and why it's actually a pretty important parameter. Before we get to that, we're going to do a little bit of history. And so what I want to do is give you a bit of an overview of how siderophile elements came into the world of geochemistry and how they have progressed through the decades. And so an important aspect of siderophile elements is that aside from people studying ores, the advance of siderophile element geochemistry among geochemists was pretty sluggish. And so it was added slowly to the repertoire of geochemical study. And there are reasons for that. And one reason, not surprisingly, is most of these elements are elements that, at least in normal rocks like granites and basalts, are in really low abundance. And so that makes them difficult to measure. Secondly, a number of these elements are very difficult to ionize using the traditional mass spectrometric methods that were used in the 1950s, 60s, 70s, and on into the 80s. And in part, in an example like for the element osmium, has an extremely high first ionization potential. So if you were using a thermal ionization mass spectrometer in 1975 and you put some osmium onto a filament and heated it up, you would essentially ionize virtually 0 atoms of it. And so what that means is any isotopic systems associated with most of these siderophile elements really didn't advance until the 1980s and 90s. And then finally, most of these elements end up being cited in trace phases, and consequently, in terms of modeling siderophile element behavior as a function of igneous processes, it's not so easy. So to some extent, we've overcome all of these issues, and we can progress. So I'm going to argue here that the holy grail of siderophile elements, if you were sitting there in the 1970s, is osmium isotopes. And this is part or an element associated with an isotope system that I've worked on for more than, I don't even want to do the math. So the isotopic system associated with osmium isotopes is that of rhenium-187, one of the highly siderophile elements, decaying to osmium-187. Osmium is a highly siderophile element as well. And this is a long-lived radiogenic isotope system. So rhenium-187 has a half-life of 42 billion years. So this is a very long-lived system, a very sluggish system. And it's important because it reveals the long-term ratio of these two highly siderophile elements. So if you have something that formed, like the mantle, early in Earth history, this records the rhenium-osmium ratio of that system with some modifications to it over 4.5 billion years. And we'll see how that is useful to us in a few minutes. So, osmium is a perfect example of a siderophile element that was really difficult to examine from an isotopic standpoint. And so this is a slide that shows some of the methods that were used over the years to try to get isotopic data for the rhenium-osmium system. And it includes electron bombardment, which you've probably never heard of before. It includes accelerator mass spectrometry, which is possibly the worst use of an accelerator mass spectrometer ever envisioned. And it also included the use of fairly early stage ion probes, not in the sense of the use of ion probes today, but in these applications that I'll show you, osmium and rhenium were chemically separated from some matrix deposited on a silicon wafer, and then the beam of the the secondary ion mass spectrometer was used to sputter off charged particles for analysis in the ion probe. Sounds horrible, right? And it was. Nevertheless, some interesting and useful work was accomplished even as early as the 1960s. So this is a example of a paper that was published, in this case in 1963, by a German-Swiss group of authors. And it was, to my knowledge, the first detailed study of the rhenium-osmium system in meteorites. And they also examined some terrestrial mantle-derived osmium iridium alloy grains, which back then you could call osmiridiums, but if you call them that now, you will get nasty letters from a guy in Canada saying there is no such thing. And so this table up here shows you some osmium 187, 186 ratios. Notice that the isotope symbol is on the right because the world was in black and white back then, and also the world insisted on the isotope numbers being on the right rather than the left-hand side back then. And so the left-hand side of that table are all for iron meteorites. The right-hand side are osmium isotopic compositions of these alloy grains. And this study reported the very first pseudo-rhenium-osmium isochron. So this is a plot of rhenium-187, osmium-186 versus osmium-187, osmium-186. And you're probably wondering what these boxes are. They are the error envelopes for the different analyses, which are huge, massive, very large compared to what we can do today. Yet, if you take the slope from this study, it's actually pretty close to what you would get using modern techniques to measure iron meteorite rhenium-osmium systematics. Okay, if we advance about 7 or 8 years, next what I consider to be really important advance with regard to this system was this one by Riley and DeLong, which interestingly enough was published in the International Journal of Mass Spectrometry and Ion Physics, even though these authors didn't do a single analysis of their very own. In fact, what they did was they took the data from the 1963 paper and innovatively plotted it versus time before present. So these are all the alloy grains that came out of the terrestrial mantle. And so this was really the first paper to argue that the rhenium-osmium ratio of the terrestrial mantle was chondritic. And you can see that in their abstract. It says a mantle osmium-rhenium ratio comparable to that in chondritic meteorites. satisfies common isotopic abundances. Now that's a really important observation, certainly for 1970, because it says that somehow the amount of rhenium and the amount of osmium that ended up in the terrestrial mantle retained chondritic proportions, even though the vast majority of these two elements got extracted into the core. You do experimental work, you would be hard-pressed to find two elements that partition between metal and silicate in such an exactly similar manner that you would end up in the highly depleted silicate fraction, in this case, with a chondritic ratio. Okay, moving on another 10 years. This is a 1980 paper by Claude Alleg and Jean-Marc Luc. And what they did was very typical of osmium research, which is they just completely redid the experiments of the 1963 paper using a higher precision technique. In this case, the ion probe technique that I mentioned to you. And so these are essentially the same osmium-iridium alloy grains that were looked at in the 1963 paper. These guys also measured the rhenium-osmium systematics of iron meteorites and generated an isochron that was considerably better than the 1963 one, and that allowed them to define the initial osmium isotopic composition of the solar system. So put these all together, you still have mantle that evolved with a chondritic rhenium-osmium ratio. Now again, you may be saying, that's not very exciting. I've been taught that the Earth is, broadly speaking, chondritic, and samarium neodymium system, for example, is broadly chondritic in the mantle as well. But again, keep in mind these are two highly siderophile elements, so it's really difficult to envision a formational process that would end up in a chondritic ratio. And then finally, I'm getting out of the history part, the 1980s were a good time for analysis of all of the highly siderophile elements, particularly as techniques to measure concentrations of these elements advanced, particularly by a process called neutron activation analysis, where you put the sample in a reactor, you make it radioactive, and you count the particles given off. So this is an example of a paper in which the behavior of, in this case, highly siderophile elements were explored with regard to petrogenesis of common terrestrial rocks. And they also reported that the relative abundances of the other highly siderophile elements were in broadly chondritic abundance. Okay, now here's a personal part. What did I do for my PhD dissertation? No one in here knows. I worked on granites. And I worked on the very same granite that Mount Rushmore is carved out of. And in fact, I also worked on granitic pegmatites. This is a big crystal of a single potassium feldspar grain. What does granite have to do with highly siderophile elements? Absolutely nothing. So they tend to have very, very low concentrations of these elements. When I nearing completion of my PhD, however, I was looking for a postdoc project, and for reasons I won't go into, I was visiting the National Bureau of Standards, which again has become the National Institute for Standards and Technology, or NIST. And at the time they built mass spectrometers there, and at the time they did innovative mass spectrometry there. And one of the mass spectrometers they showed me was this one on the left, which is called a resonance ionization mass spectrometer. And what it did was it used laser light, highly tuned laser light of a very specific wavelength, to photoionize neutral atoms. And so I was told this was a mass spectrometer that could atomize an element like osmium or rhenium and then ionize it using the laser light, which you can see bending around here going into the front end of a mass spectrometer. So the good news is it worked. The bad news is it was a very imprecise and very non-sensitive method, but you know, we were happy about it. And just to convince you that even if you don't sometimes get the highest precision data, you can sometimes do some really neat stuff with it. These are 3 papers that got generated out of my postdoc work and a subsequent postdoc with the Carnegie Institution of Washington. We were the first to measure the osmium isotopic composition directly of chondritic meteorites. So that is this paper here. We were the first to actually generate a genuine terrestrial isochron, in this case for some komatiites from northern Canada. And we were also first to demonstrate that osmium isotopic composition of peridotite xenoliths from subcontinental lithospheric mantle could tell us about the melt history, particularly when the melting occurred, in materials underlying continental cratons. And in this study, we looked at xenoliths from the Cap Val craton and found that the underlying lithospheric mantle had the same 3 billion year age as the overlying crust. So these were pretty good advances for measuring something to plus or minus 1%. And then everything changed in the 1990s. So in early 1990s, this paper was published, Negative Thermal Ion Mass Spectrometry of Osmium, Rhenium, and Iridium. And this was a paper that essentially explained how you could use certain techniques to generate negatively charged trioxide species of osmium and rhenium and measure them using essentially a conventional thermal ionization mass spectrometer. The only trick was you were creating a charged molecular species, and it was a negatively charged molecular species. Hence, you had to have a mass spectrometer that had a switch that says negative ions, that says positive ions. A Frankenstein switch. You could change from positive ions to negative ions. And it just so happened I had a mass spectrometer that enabled you to do that. A bunch of labs had commercial instruments that didn't allow switching from one to the other. So, they didn't get to do osmium isotopes. Also, the 1980s were really the advent of commercially available inductively coupled plasma mass spectrometers. And by the end of the 1990s, there were at least 3 manufacturers even of multiple collector ICP mass spectrometers. And that allowed measurement in particular of the other highly siderophile elements. I would still argue that N-TIMS is the best way to measure osmium, but we measure the isotopic compositions and hence the abundances of other highly siderophile elements almost exclusively using ICP-MS now. And so that's really where we are. Things haven't changed in 30-some years. We have refined techniques, but the techniques that were available by the early 1990s are really still what's being used. I think I said that. So early 1990s, modern times arrived. Okay, so let's get on with the topics. So the first topic that I want to talk about is the origin of siderophile elements in the bulk silicate Earth, everything exclusive of the core. And what I'm going to try to convince you in a few slides is that the dominant process responsible for moderately siderophile elements, remember that includes tungsten, molybdenum, cobalt, nickel, was probably different from the dominant process that established the highly siderophile elements like gold, platinum, and osmium. You're probably skeptical, but that's okay. So, your computer does that. That's great. I mean, I knew Rutgers was a great place, but animation never works. So let's talk MSEs. So this is a plot of both MSEs and HSEs. The MSEs are the green symbols, and they are arranged from most refractory to most volatile. Germanium of this list is the most volatile. And then rhenium down to gold, with rhenium and osmium being most refractory of the highly siderophile elements, and gold being the most volatile. So a couple things to notice. This is a plot of their estimated abundances in the bulk silicate earth, the BSE, ratioed to C1 chondrites, the conventional reference frame for most things. You can see that all of their abundances are less than 1 times Ci chondrites. That's not surprising. They are siderophile elements, so they are largely sitting in the core rather than the bulk silicate earth. You'll also notice the relative abundances of the green symbols kind of vary quite a bit. So that means relative to Ci, there's quite a bit of variability in evidently what was extracted into the core relative to the silicate earth. So in the 1990s, there were a number of papers exploring this issue. This is a particularly famous one by Jackie Lee, who is now at Michigan, I think, and Carl Agee, who was at Harvard at the time. And basically, it's a paper that argues to achieve the cobalt-nickel ratio of the terrestrial mantle or bulk silicate earth. And remember, both cobalt and nickel are moderately siderophile elements. You can't do it under low pressure conditions, but you can achieve the ratio that is observed in bulk silicate earth if you do it under high pressure, high temperature conditions. And so I think the 1980s and 1990s were the beginning of increasingly higher pressure and temperature experimental work being done. And so they argued at the end of this paper that the most likely scenario to give us the nickel-cobalt ratio that we see in the bulk silicate earth is metal silicate partitioning at a depth of something on the order of about 800 kilometers down. So at considerably higher pressures and temperatures than experimental work had been done previously, more likely at 1 atmosphere conditions. And so that has kind of evolved into a cartoon sketch. This is used everywhere now, it seems. This is a nice, they chose nice colors for this too, I have to say. So this is from Wade and Wood from, oh boy, that's going on 20 years ago. They're arguing in this paper that as the Earth accreted and neared its final mass, metal pooled at a depth of, again, something on the order of 800 to 1,000 kilometers down. And this is where metal silicate partitioning occurred. And then the metal eventually bled down through a solid lower mantle to be incorporated in the core. I should point out this is all magma ocean, at least as they envisioned it. And so this is a way of distilling moderately siderophile elements into the core, which is kind of an interesting concept. But in addition to that, calculations suggest that really the molybdenum, tungsten, cobalt, nickel that's present in the silicate earth today was largely added during the final 10 to 20% of planetary accretion. So later on, I'm going to tell you where the molybdenum came from that's in your body and is sitting around you in this room. But what I'm really talking about here is, the molybdenum that is present as accreted to the earth during what we call later stages of accretion. And this is just the plot showing that you can actually match pretty much all of the moderately siderophile elements by appealing to high pressure temperature partitioning of these elements. This is a figure from Kevin Ryder. Oh, that works too. So now let's move on to the highly siderophile elements. So the highly siderophile elements in this figure look very different from the moderately siderophile elements. First, they occur in much lower abundance. That's why they're called highly siderophile elements. They're more favorably partitioned into metal compared to silicate. Also, they kind of occur along a horizontal line. You can almost draw a horizontal line through these data. So by and large, they are roughly in chondritic relative abundance, which we've already learned is what osmium tells us. We're going to see that again. It also is consistent with the studies of highly siderophile elements in mantle rocks in those 1980s studies. Oh, here's this figure again. So what's the point of this figure? This is where animation again comes to work for me. To get from here to here and hit the bullseye, which is chondritic, it tells you you have to have a exactly chondritic rhenium-osmium ratio. Pretty much exactly chondritic rhenium-osmium ratio. And in fact, chondrites aren't all the same when it comes to osmium isotopes. So this is a histogram we published, I don't know, 15 years ago. It hasn't changed any, in which we're plotting osmium isotopic composition now, osmium-187, osmium-188. I didn't mention, but we switched from osmium-187, 186 to osmium-187, 188 towards the end of the 1990s, when it became apparent that osmium-186 is actually a radiogenic product of an isotope of platinum. The thing to note here is, unless you're colorblind, you'll see that there are 3 different colors for chondrites, with the red and the green being ordinary and enstatite chondrites, 2 types of chondrites that we believe formed, for reasons we won't go into here, in the inner solar system. And the blue represent data for carbonaceous chondrites, which many people believe formed in the outer solar system. The best estimate for bulk silicate earth is here. And you can see that in this case, the bulk silicate earth value is a really perfect match for ordinary and enstatite chondrites. It's not a perfect match for carbonaceous chondrites. Now this is interesting because it suggests that the osmium contained in the bulk silicate earth largely came from the inner solar system. And this is a confusing diagram, I'm sorry, but you need to see it. It's just a plot. In this case, it's no longer a logarithmic plot, it's a linear plot, showing that the abundances of all the other highly siderophile elements, when doubly normalized to C1 chondrites and iridium, are a pretty good match for chondrites. The bulk silicate earth is a pretty good match for chondrites, possibly with the exception, I should point out, the star is bulk silicate earth, possibly with the exception of a minor anomaly in ruthenium and maybe a little bit of one in palladium. So again, just like we learned in the 1980s, the relative abundances of these elements really looks chondritic and of a specific type of chondrite. So the obvious question is, I told you a few minutes ago that moderately siderophile elements had their abundances established by high pressure temperature partitioning, maybe about halfway down in the mantle. Can we do that with highly siderophile elements to explain their abundances? And the answer is no. And the reason for that is the partitioning between metal and silicate for the different highly siderophile elements is quite different from element to element. And so under various pressures, 5 GPa, 20 GPa, 40 GPa, 60 GPa, where this study did experimental partitioning between metal and silicate, you never end up with something that looks like bulk silicate earth pattern here. Again, this is all plotted ratioed to C1 chondrites. So occasionally somebody pops up and says, oh, I can find a condition that matches the concentration of one of these elements in the mantle. My response is, can you get rhenium and osmium to exactly agree to chondritic in your experiments? And they say, no, we can't do that. So I don't listen to them. So what's the alternative? Probably the best alternative, at least in my view, is something called late accretion. And so late accretion refers to the addition of a final 0.5 to 1% of Earth's planetary mass by the impact of smaller objects that are either sufficiently small, well, let's just say that are sufficiently small that their metal components, if they have metal components, never make it to the core. So you've got little guys smashing into the Earth, they're mixed into the mantle, And if they have metal containing highly siderophile elements, that never makes it to the core. And so it's a way of re-enriching the silicate shell of a planet in highly siderophile elements. And it's certainly a good way of ending up with chondritic relative abundances, because that's what's really defining their abundances. You may even be more familiar with the term late veneer. Late veneer is a term I don't like because that refers to stuff being added to the surface. This is not necessarily stuff added to the surface. What you really need is something on the order of 1 or 2 Pluto masses added to the mantle. If you have something that big, that's not a surface phenomenon. Okay, so some amount of late accretion is dynamically even expected. And what that means is, if you are a person who does planetary dynamical modeling of early solar system formation and planetary growth, you don't immediately go from having a bunch of stuff that's accreting to nothing that's accreting. In fact, you can still walk outside and get hit on the head by a meteorite, right? That's not much accretion, but it's still happening. And so lots of calculations have been done. This is one from a guy named Simone Marchi from about 10 years ago. This was, these blobs represent the essential sizes of bodies left over after he envisioned lunar formation. And so there's a lot of stuff still lying around ready to be accreted to a planet even after core formation ceases. At least that's what they tell me. That's not what I do, but it makes sense. Okay, so let's make some conclusions. So I think there's really, really good evidence that the moderately siderophile element abundances in the bulk silicate Earth were in fact established as the Earth grew under comparatively high pressure and temperature conditions where metal and silicate equilibrated. And an addendum to that is, because of the way these materials would have been added to the Earth, the moderately siderophile elements by and large were added to the silicate Earth during the last 10 to 20% of planetary accretion. So they don't, what they tell us about the earliest primordial Earth, the stuff that was there during the first 80% of accretion, it doesn't tell us much about them at all. Secondly, the osmium isotopic composition of the terrestrial mantle, as well as the relative abundances of the highly siderophile elements, are really difficult to explain by a process, I argue, any other process than late accretion. So I'm still unimpressed by other arguments I've heard for other processes. I think late accretion is still the best explanation for why we have the abundances of platinum, osmium, gold in the silicate Earth that we do. And I want to bring in a little bit of history again. This is not a new concept. These were concepts that evolved in the 1960s and 1970s, albeit at that time there was not the experimental or analytical abilities to go as far as we just went with arguing these points. And so I show you this figure from a kind of famous paper from 1978 by Chow. And in it, these are direct quotes, he says nearly chondritic ratios of noble metals, well, that's actually what we're calling highly siderophile elements, is interpreted as derived from meteoritic influx during late heavy bombardment. Well, I wouldn't call what we called late accretion late heavy bombardment, but it's really the same concept. And then with regard to moderately siderophile elements, which are the nickel, cobalt, germanium group over here, he argues they appear related to indigenous mechanisms, including the effects of high temperature and pressure at the core mantle boundary. Well, it doesn't have to be the core mantle boundary. We have better constraints on that now. But again, he got the idea right in 1978, and it took a couple decades, I think, to really convince everybody else of this. But wait, you're probably sitting there going, if late accretion established the abundances of highly siderophile elements in the bulk silicate earth, why didn't it do the same for the moderately siderophile elements? I wanted to make sure you didn't go home thinking, gosh, why didn't I ask that question? The answer is the abundances of moderately siderophile elements left in the silicate earth after core formation ceased was much higher than highly siderophile elements. So late accretion does add moderately siderophile elements to the silicate earth. It's just that they're diluted much more. And so late accretion would add roughly about 10%, for example, of the tungsten budget to the silicate earth, compared to essentially 100% for the osmium. Okay, topic 2, tungsten isotopes in the modern mantle. What I just told you is nothing new. So I could have given that talk, and in fact I've given 2 talks here before. I probably did give that talk before here, but you guys can't remember that. Topic 2 is something a little bit more topical. So this is really ongoing, what I would consider pretty hot research. So I'm going to just spend a few minutes talking about the hafnium tungsten system. It's a very short-lived system in contrast to rhenium osmium. This is a system that was extinct 50 to 60 million years into solar system history. Notice I say in the modern mantle, so you are probably sitting there going, this system was dead before the Earth was even fully formed, so this should be a pretty boring topic to discuss. But it's not. And just to give you a blueprint of how this planet works, hafnium is a strictly lithophile trace element. Tungsten is a moderately siderophile trace element. So all of Earth's hafnium is sitting in the silicate Earth, and about 90% of Earth's tungsten is sitting in the core. And interestingly enough, the tungsten isotopic composition, if you want it, 182-184 tungsten ratio, which I'm going to talk about in terms of the mu182 value. This is parts per million deviation in this ratio from standards that we believe are representative of bulk silicate Earth. Because you are a human and you like to define things in terms of your own perspective, we've defined bulk silicate Earth and ourselves as having a value of 0. That makes you feel comfortable. It's good to be a 0. Again, mass balance argues then that the core has about a 220 negative or a deficit in tungsten 182 compared to you and me and light bulbs of yesteryear. I guess modern light bulbs don't have tungsten in them. I don't know. So from a cosmochemical standpoint, this is a system used to date metal silicate segregation. And it's also then obviously a system that is potentially useful for documenting core mantle interactions. And so let's look at ocean island basalts. Why would we go to ocean island basalts? Well, as I just showed you, the core is the one place inside the Earth I'm really pretty confident has a very different tungsten isotopic composition from you and me. And we said it's more than a 200 part per million deficit. Seismic tomography, everybody knows what seismic tomography is. Seismology applied to planetary-wide processes, looking for seismic waves that go faster or slower in interior portions of the Earth. Suggest, you should take a course on this, it would be good for you. Seismic tomography suggests that a number of ocean island basalt systems are underlain by plumes, hotter material than the ambient mantle, that in some cases rise from the core mantle boundary. So if ever there was a type of material where you'd want to go looking for a core mantle, evidence of core mantle interaction, probably an ocean island basalt might be the best place, right? Sure. And some ocean island basalts are really nice to go visit. So this is a picture of Hanama Bay in Oahu. And so, yeah, it's a good place to go looking for an extinct system anomaly. Even if you don't find it, you'll have a good time. So this is not a novel idea. This is not a new idea. We've been talking, I've been talking about this for more than 20 years. In this paper from essentially 20 years ago, these authors measured the tungsten isotopic composition here. It's in epsilon units, which is parts per 10,000, in some Hawaiian lavas that we thought may have a core component based on osmium isotopes. We won't go into that. You can see the title of their paper, Tungsten Isotope Evidence that Mantle Plumes Contain No Contribution from the Earth's Core. Very definitive statement. So move on 15 years later, 10 years later, whatever it is, 12 years later, I had a postdoc named Andy Mundell who worked on tungsten isotopes in terrestrial rocks. And she actually found a bunch of anomalies pointing in the right direction, lower tungsten isotopic ratios than we expected for at least from standards. And she found these so-called anomalies in rocks from Samoa, an ocean island basalt system, Hawaii, and possibly from Iceland. So these results were published in a science paper in 2017. And the good news is the anomalies are in the right direction. They are negative anomalies, and the core is way over here on the left, my left-hand side of the room. And even more incredibly, and this is really pretty hard to explain, she found a correlation between tungsten and helium. Helium, you've hopefully been taught, is a noble gas. And helium-3, helium-4 is an interesting ratio because high helium-3-4 ratios in particularly ocean island basalt systems have been interpreted quite frequently in the literature as evidence of a component in the ocean island basalt system that was very primitive and undegassed or less degassed than the rest of the mantle. So we have two pieces of evidence here for something that formed really early and hasn't been doing much in the mantle ever since. Remember, tungsten is a system that's been dead longer than I've been alive, longer than you've been alive. Okay, so what does this mean? Well, that paper interpreted that trend as being two-component mixing between something that looks positively boring and normal and a component that has a significantly negative tungsten 182 anomaly and a high helium-3-4 ratio. And again, helium-3 is a primordial isotope of helium. Helium-4 is, of course, also partially primordial, but it's also produced by the decay of uranium and thorium. And so if you have a lot of uranium and thorium in some recycled material, you lose high helium-3-4 ratio. If you degas something and then you grow in more helium-4, you also lose high helium-3-4 ratios. So high helium-3-4 really implicates something isolated pretty early in Earth history that has not experienced much in the line of recycled crustal components in it, at least from a plate tectonic standpoint. And again, with regard to low mu-182 tungsten, you've got to have something that formed within the first 60 million years of solar system history, not even Earth history, but solar system history. And that could be the core, or it could be some fractionate of an early silicate differentiation event. But if you want to appeal to an early silicate differentiation event, A, you have to do it early, and B, you have to hide it somewhere for 4.5 billion years, which is a long time. This talk may seem like it's very lengthy talk, but 4.5 billion years is longer even than my talk. Okay, so now that's interesting. The zero gray bar disappeared, but that's okay. So Andy Mundell continued on, although she became Andy Mundell Petermeyer, and she published these data for a whole lot more ocean island basalts in 2020. the thing to see is that there's quite a lot of ocean island basalt systems with negative anomalies. And in fact, when you plot the data for the different systems up versus helium, you start seeing different trends, or different trends with different slopes. And so the tungsten 182, helium 3,4 ratio data for different ocean island basalts define different trends. That would be potentially different mixing trends. And this yellow bar here represents rocks from the Galapagos Islands, and that's as far as, well, I won't go into it, but that's the steepest trend in this figure. Now, reviewers didn't like calling those things trends, so if you don't like that as being a statistically significant trend, that's fine. What this really requires, though, is that you have at least 3 isotopically distinct sources being mixed in these ocean island basalt systems. So just briefly, component 1, which would be up here, looks just like ambient upper mantle. I didn't show you the data for it, but there are some really high helium 3,4 ratio samples in West Greenland associated with continental flood basalts. They actually don't have tungsten anomalies, so you have to appeal to a component that retained a high helium 3,4 ratio, but it must have formed after hafnium 182 decayed away. And then component 3 is a primordial signature that tells us something is down here. Okay, so what is it? Are we directly taking some metal from the core and putting it into the lower mantle? No, we don't see higher highly siderophile element abundances, which are really enriched in core metal. So we don't think that's the case. And our current, at least my current interpretation is that we have some sort of isotopic equilibration or isotopic exchange between the core and the base of the mantle. And this is a mixing diagram, which we don't have to go into, but by and large, it doesn't take much of a core-like component to create the 3-component mixing diagram that is required for these data. So this is where we get to the wild speculation part of the talk. The ambient mantle is probably component 1. Component 2 has a lot of recycled component in it. Perhaps, at least some people have argued with this. We don't have time to talk about seismology. These have been argued to be associated in some cases with large low shear velocity provinces, also known as LLSVPs. And at this point, I'm putting my money as component 3 being on also seismically identified blobs of stuff at the core mantle boundary that are termed ultra low velocity zones, or ULVZs. And this is kind of a schematic diagram showing how we think LLSVPs, which are much larger features than ULVZs, may be contributing high helium 3,4, and ULVZs may be contributing the tungsten. Okay, I've just got a couple minutes left. I'm going to briefly talk about molybdenum isotopes and why it's the ideal genetic tracer element for late stages of Earth accretion. And I'm assuming Kath has taught all of you about different nucleosynthetic processes. If she hasn't, you need to take a course that looks at nucleosynthetic processes. So again, molybdenum is a moderately siderophile element. As we saw, molybdenum was likely added during the final 10 to 20% of Earth accretion, and it's one of the few elements that allows distinction between S, R, and P process stellar nucleosynthesis. We could go on for hours about that. She can. So why is molybdenum so exciting? Molybdenum is exciting because isotopic variations in molybdenum were one of the first demonstrations of different genetic components in cosmochemical materials. So this is an incredibly important paper published by Nicolas Dauphin in 2002, in which he showed the molybdenum isotopic compositions of different iron meteorite groups, i.e. different planetesimals, varied as a consequence of non-mass independent non-mass dependent processes, and consequently the differences represent different building blocks for those planetesimals. And this has evolved into a figure that those of us that do cosmochemistry have perhaps seen too many times. This is a plot of molybdenum 94 in part per 10,000 deviation from terrestrial versus epsilon 95 molybdenum. These are produced largely by different processes, so it's very interesting to note that different types of meteorites plot along two different linear trends. And now the convention is the upper trend is blue and refers to something that is called a carbonaceous chondrite type reservoir, or CC, and the red is termed non-carbonaceous, or NC. And it's kind of generally assumed by most people that the red stuff, the NC material, is inner solar system material and the blue is outer solar system material. Why should you care? Have any of you had your DNA tested? Have any of you had your dog's DNA tested? Well, you're wasting your money, because I'm going to tell you what your genetic heritage is, and you don't even have to spit into a container to find out. Okay, so how do you do this with molybdenum isotopes? Well, this was from a paper by Garrett Buda from 2019. This is the NC trend that I just kind of showed you. It's kind of cleaned up a bit. Here's the CC trend. And they measured a bulk silicate earth composition for molybdenum that plots essentially right between these two parallel trends. And with that, they argue in this paper that the Earth's silicate Earth's molybdenum is a roughly 50-50 mix of CC and NC. So they would argue that's really the genetics, at least of the molybdenum of your body. And that's very important, because CC materials are believed to have formed in the outer solar system. Outer solar system materials are commonly water rich and organic rich. And so this is one possible means of delivering water and organics to the Earth. Okay, so this brings in your colleagues, Kath and Hope Tornabene. Does everybody know her? She's your employee. Anyway, there they are. So Hope hopefully is running a mass spectrometer right now. To make a long story short, we have collectively been analyzing a whole bunch of terrestrial samples, including molybdenites. That's what this cluster of data are. The red line represents still NC trend. The blue still represents the CC trend. We've also been reanalyzing some iron meteorites to more precisely and better define the slope of the NC trend. And to make a long story short, we're about to submit a paper that argues that actually the bulk silicate Earth plots within the error envelope of the NC trend. And that's important, because that says that all of the later accreted molybdenum during the last 10 to 20% of Earth's accretion came from the inner solar system. If you are familiar with and believe in a giant impact to form the moon, this would also argue that the giant impactor, Theia, some people call it, also is derived from the inner solar system. So a completely different interpretation. Why are we different from the 2019 study? Yeah, that's a long story. Who will come out on top? I don't know. Anyway, you paid good money for finding your genetics when you think you're a scarlet knight, but actually you are an NC. And so here's the summary. I think we've discussed all this. Osmium isotopes really, I think, define late accretion as being material derived very much so from the inner solar system. Tungsten isotopic heterogeneity in modern ocean island basalts tells us that some really, really ancient reservoir is still sitting inside the Earth somewhere and contributing to mantle plumes. The good news is we know of one such reservoir, and it's called the core, and it has a lot of tungsten in it. So that's my favorite explanation. And then finally, the molybdenum isotopic composition, if we are right, is telling us that the final 10 to 20% of Earth accretion was of inner solar system material rather than a significant quantity of outer solar system material. Okay, I went over by 5 minutes, but that's life. Thank you.
Well, thank you for that illuminating talk. Questions from the audience, and let's start with the students.
Oh, they hate that.
Oh, but they're prepared. Brilliant.
So you think that, I'm pretty sure from what I know, like the water composition has a deuterium hydrogen composition close to CC meteorites.
Mm-hmm.
You've shown that most likely most materials from the inner solar.
It actually depends on a number of things, one of which is how much water do you think is present in the Earth? So 4 oceans worth is a common number bandied about. This doesn't specifically state you can't have any CC contributions. It just suggests that it's not a substantial component. Whether or not you can add enough water by that process to give you 4 oceans worth of water is questionable. So, don't know. Different systems tend to tell you different things. Molybdenum, at least in our view, seems to tell us a dominantly inner solar system origin.
Other questions?
So there are a lot of assumptions of isotopic composition and elemental composition built on our meteorite collection. Do we believe that our meteorite collection represents polar range, at least, of possible compositions, or we expecting some extreme members that we didn't find or will not ever find?
My immediate response is heavens no. So when you talk about meteorites, you're talking about largely rocks that fell from above during the last few thousand years. So lots of the materials that were present in the early solar system, of course, aren't even there in the asteroid belt anymore. So yes, I believe you know, the future of your life in science will reveal all sorts of exciting future variations in isotopic compositions, and so I'm not even confident that things that plot on CC and NC trends should all be plotted on CC and NC trends. So yes, lots of fun research in the future.
Thanks, Rich. That was really interesting. I'm wondering for your point 3, whether it's a plausible alternative hypothesis that in addition to the accreted materials that are setting the HSEs, there's something else that's very HSE poor, but that's still accreting during the last 10 to 20%.
That certainly is possible. In this case, we're talking moderately siderophile, not highly siderophile. But you know, if you were taking mantle material from a differentiated planetary, planetesimal, something Pluto-sized, and got rid of the core, you know, you don't have much of a lever arm to change the isotopic composition of molybdenum, which would be good if the rest of the body were CC. So, you know, it's something that has been argued in the past and undoubtedly will be argued in the future. Did that answer your question?
Yeah, I think I was thinking about the volatile delivery history and whether there's
So I should say the history of water and volatiles has always been problematic, because if you're accreting a hot planet, retaining the volatiles, especially water, is not so easy to envision. And if you have giant impacts, it's not so easy to envision retaining volatiles or allowing organics to survive. And yet here we are, we're made of water and organic stuff. So different studies have tried to explain it in different ways. One alternative explanation for water, which is really hydrogen with some oxygen attached to it, is ingassing of hydrogen during initial stages of Earth's accretion. I'm agnostic with regard to that. I only talk about siderophile elements, so I avoid talking about water and organics other than you can't argue that late accreted materials were exclusively CC because they don't have isotopic signature of a CC material.
Any other questions?
Nice talk, thank you. How could the Earth be made of instantite chondrites? I know that's not the only possibility, but if it was, then the mantle should be instantite rich rather than olivine rich.
Well, I would not ascribe to an Earth that's an instantite chondrite.
Okay.
I would not ascribe to an Earth that is an instantite chondrite, yet, genetically speaking, Earth is a pretty good match to instantite chondrites in terms of a number of different elements, which has been noted by lots of people. Genetics does not equal chemical composition, and so I would argue that it doesn't trouble me that the Earth has an isotopic composition similar to instantite chondrites. It's not a perfect match, but that it would be chemically significantly different. So you need not be troubled about that, in my view. Actually, the closest genetic match from a siderophile element standpoint to us are group 1AB main group iron meteorites, which nobody talks about because nobody understands them, but they are the best genetic match to us. They're better than instantite chondrites. So if you're fearful of the Earth being an instantite chondrite, you should fear even more that we're really an iron meteorite.
Any other questions? Okay, I think on that note, we will wrap it up. So Rich, thank you very much.
Sure, thank you.